Jai Hind to all. My name is Divya Sharma and today's video lecture is on wave propagation. So this is the topic in which we will discuss field strength relationship. It is the space wave propagation. So here you can see this is the transmitter, this is receiver. So when we are sending signal from transmitter to receiver, so there are two ways. First is direct wave and second is the indirect method, right? So indirect method, we are sending signal directly from transmitter to receiver, and in the indirect method your signal is transmitting from transmitter to first it is goes to ground, then it is reflected back to the receiver. So this is indirect method. So this is the propagation of space wave over flat earth. Now here both waves undergo attenuation. It means here attenuation is negligible here as they travel through space as spreading and rain. So it is important to mention here that only high frequency waves are attenuated by the rain. Now field strength relationship, so both the waves undergoes attenuation as they travel through space as spreading and rain. It is important to mention here that only high frequency waves are attenuated by rain. Now field strength of each wave is inversely proportional to the distance from the transmitter, provided the transmitter and receiver antennas are as far from each other. Now further, the distance d should be greater than the antenna's height. Therefore, the angle of incidence from the ground reflected wave at the surface of the earth will be small. At receiver antenna, the magnitude of two waves remains the same, but the phase reverses irrespective of the type of the polarization. So these are the points we have to consider here when we are studying the field strength relationship. Now, how we can study mathematically? So from the figure, previous figure, the path R1 is given by, so R1 is equal to what? RT, this is the height of the transmitter, this is the height of the receiver plus distance between the transmitter and receiver. So R1 is the path we have to calculate. R1 square is equal to HT minus HR square plus D square. So here we can take common D from this term to this term. So we are taking common here D. So what we will left here? 1 plus HT minus HR ka square upon D square ki power 1 by 2. Now this is nearly equal to D in bracket 1 plus HT minus HR ka square upon 2D square. This is by the using binomial theorem. So here R1 is equal to what? D plus HT minus HR ka square upon 2D. So this is R1. Now similarly we can calculate by this method, we can calculate R2. R2 is equal to what? R2 square is equal to HT plus HR ka square plus D square. Now here we can take common D. So here also again we are applying here binomial theorem. Now after applying this binomial theorem, we will get here R2 is equal to D plus HT plus HR ka square upon 2D. So what is the difference in R1 and R2? You can see here this is negative sign here, this is the positive sign. So this is your R1 and this one is R2. So in order to calculate the field strength E at the receiver, we should know the phase difference between the reflected wave and the direct wave reaching at the receiver. So first of all, we should calculate the path difference between these two waves. Waves are direct wave and reflected wave. Now path difference. So we have to find out the path difference R2 minus R1. So we can put this value R1, R2 in this equation and we can find out the phase difference. So phase difference is represented by del S, that is equal to HT plus HR ka square upon 2D minus HT minus HR ka square upon 2D. So we can calculate it and finally we will get here 2 HT HR upon D. So this is the path difference. Now the phase difference corresponding to this path difference is equal to what? This is the formula to how to find out the phase difference. So phase difference, so alpha is equal to 2 pi upon lambda into phase difference, path difference. Path difference is represented by del S. Here we are calculating del S. So you can put here this value del S and you can find out the phase difference. So alpha is equal to 2 pi upon lambda. So put here the value of del S, that is 2 HT HR upon D. So put here this value and you will get alpha phase difference is equal to 2 pi HT HR upon lambda D. This is in radian. Now phase difference due to the reflection from the ground, that is equal to beta is equal to 180 degree. Now total phase difference, how we can calculate? So total phase difference is denoted by delta is equal to alpha plus beta. Beta you all know that is equal to 180 degree. Now alpha plus 180 degree. Now resultant field at the receiver due to field strength of direct wave is represented by field strength, direct wave is represented by ED, and the field strength of reflected wave is represented by ER. So resultant field is equal to what? Resultant field is equal to direct ray, field strength of direct ray and field strength of reflected ray. So E is equal to ED plus ER. Now here we are getting the exponential term e ki power minus j alpha plus 180 degree. So this is the total phase difference. Now here ED is equal to ER is equal to ES. So therefore we will get here E is equal to ES 1 plus e ki power minus j in bracket alpha plus 180 degree. Now we can apply here exponential term, we can replace it by using the terms of cos and psi. So that is equal to what? E is equal to ES in bracket 1 plus cos alpha plus 180 degree minus j sin alpha plus 180 degree. Now we can reduce it and we will get here the value E is equal to ES in bracket 1 minus cos alpha plus j sin alpha. Now here find out the magnitude of E. Magnitude of E is equal to ES under root 1 minus alpha ka square. This is the first term and this is imaginary term. So real term square plus imaginary term. So E magnitude is equal to ES under root 1 minus cos alpha ka square plus sin alpha ka square. Now here E is magnitude is equal to ES under root. So open this bracket and you will get these terms. And finally here you are getting ES in under root 2 in bracket 1 plus 1 minus cos alpha. Now here finally ES is equal to under root 4 sin square alpha by 2. So put here when you are solving this, here you will get this term cos 2 alpha is equal to 1 minus 2 sin square alpha. Right. So finally we are getting here E is equal to E0 upon D. So ES is equal to E0 upon D under root 4 sin square alpha by 2. Now here substituting the value of alpha. So E is equal to 2 E0 upon D sin. You can put here the value of alpha that is calculated in the previous slide, that alpha is equal to what? 4 pi HT HR upon lambda D. So put here the value of alpha and you will get here E is equal to 2 E0 upon D sin 2 pi HR HRT HT HR upon lambda D. Now therefore the field strength E at the receiver is equal to what? 2 E0 upon D sin 2 pi HT HR upon lambda D. Now here E0 is what? Field strength of the direct wave. ST is the height of the transmitting antenna, HR is the height of the receiving antenna, D is the distance between these two antennas, transmitter and receiver. Now, for large distances, for large distances, your 2 pi HT HR upon lambda D is less than 0.5. So you can similarly you can this is less than 0.5, then sin 2 pi HT HR upon lambda D is nearly equal to 2 pi HT HR upon lambda D. So you can put here this value, sin theta is equal to what? Theta, nearly equal to theta. So you can put here theta in this previous equation. E is equal to 2 E naught upon D sin theta. So here sin theta is nearly equal to theta. So you can put here this value and you will get here E is equal to 2 E naught upon D in bracket 2 pi HT HR upon lambda D. Now here we can solve it and you will get here E is equal to E0 4 pi HT HR upon lambda D square. So E0 is the field intensity produced at a unit distance by direct ray emanating from the transmitting antenna in the desired direction. It depends upon the directivity of the antenna and transmitting power, that is PT. Now field strength relationship. So E is for a half dipole antenna placed at some distance from ground, E0 is equal to 2 to 1.4 under root P Weber per meter. So this is your electric field for half dipole antenna. Now P is the power in kilowatt. Now, and if P is the effective power radiated in watts, then E0 is equal to 7 under root P. So E is equal to what? So here this is your E0. So E0 you can put in the previous equation, that E is equal to 4 pi HT HR upon lambda D square. So here put the value of E0, that is equal to what? 2 to 1.4 under root P. and that is equal to what? 7 under root p. So put here this value of E0 and you will get here AE is equal to 82 under root p HTHR upon lambda d square volt per meter. Now effects of imperfect earth. Now following are the effects of imperfect earth. Earth is basically imperfect and electrically rough. As you all know, earth is imperfect and electrically rough. For perfect earth, reflection coefficient it should be unity, but actual earth makes it difficult from the unity. The amplitude of ground reflected ray is smaller than that of the direct ray. Next point is, when a wave is reflected from the perfect earth, its phase changes of 180 degree, but actual earth makes the phase change different from 180 degree. So expression for the field is usually derived on the assumption of no change in amplitude and phase reversal after reflection, and E0 by D is the field strength which actually correspond to direct wave. It also corresponds to the reflected wave for perfectly conducting earth. Now the next point is, field strength at a distance D is always less than E0 by D. When A is equal to CO, horizontal components of incident electric field E1 and reflected electric field ER gets cancelled at reflected surface and vertically components added together. So the field at the receiver point due to the space is reduced by Earth's imperfection and roughness. So these are the effects of imperfect Earth. Now effects of curvature of Earth. So the main effects of Earth curvature are as follows. The curvature of the Earth may not allow the direct ray to reach at the receiver, thus reducing the field strength at the receiver as shown in figure this. In shadow region, no signal reaches. This is known as shadow zone, or you can say diffraction zone. So you can see here, this is your transmitter, this is your receiver, and this is your curved earth. When you are sending your signal from transmitter to receiver, so this is the direct ray, and another signal when we are sending from transmitter, so it is reflected from this earth and it is ground reflected ray. So and this is the shaded shadow region. This is also known as diffraction zone. So field strength for this effect of Earth's curvature, field strength is equal to what? 2E0 upon D sine 2 pi HT dash HR dash upon lambda D. HT dash and HR dash are the effective heights of transmitter and receiver antennas. So we can consider here, when this is your transmitter and this is the receiver. So this is the direct ray and this is the reflected ray. This is the height of the transmitter. This is the receiver's height, receiver's antenna height, and this is the curve. Now here we are, these are your effective heights of transmitter and receiver, and that is represented by HT dash and HR dash respectively. So since the reflection at the ground take place at a spherical point rather than a flat point, hence the reflected ray becomes divergent, which results in weaker signal at the receiver point. Now the third point is, the difference in path lengths between the direct and ground reflected wave is reduced at a point of reflection on ground is raised. As a result, it tends to reduce the signal strength at the receiver point. So shadow zones are also formed due to the presence of objects such as hills, buildings, trees, etc. in the middle of the transmitter and receiver. Means this, let us consider this is your object in between transmitter and receiver. So these are considered as shadow zones. Okay. Now on the other hand, ghost images are produced due to these objects which disturb the performance of the receiver set. The shadow zone and ghost inferences are here in this figure. So you can see here, this is your transmitting antenna, this is your receiving antenna. Here this is the receiver. Now this is the shadow zone. It may be imperfection in the when you are sending your signal from transmitter to receiver. Now let us consider a question. A microwave signal of 1.9 GHz arrive at antenna via two paths differing in length by 19 meters. So calculate the difference in arrival time for the two paths. Second part is, calculate the phase difference between two signals. So how we can calculate it? First we have to find out the difference in arrival time for the two paths. So del T is equal to what? Distance upon speed, and distance is given in the question 19 meter. Speed you all know 3 into 10 to the power 8. So you will get here delta T is equal to what? 63.33 nanoseconds. Now we have to find out the phase difference between two signals. So how we can find out phase difference? As you all know the formula, phase difference is equal to what? 2 pi upon lambda into path difference, and 2 pi upon lambda into path difference, and lambda, as you all know, c upon f, and c you all know it is universal, that is equal to what? Speed of the light 3 into 10 to the power 8. Now frequency is given in the question, that is 1.9 gigahertz. So you can put all these values and you can find out, and delta s is equal to what? 19. Now here when you will put all these values, you will get here 756 radian. So this is the phase difference between two signals. Now next question is, find the maximum range for which the transmitting antenna having height of 25 meter and receiving height of 16 meter for the effective point-to-point communication. So this formula for this distance, when we are finding the distance, so d is equal to what? 4.12 in bracket under root ht plus hr, under root hr, this is in kilometer. So as you all know, this is given in the question, this is your ht and this is your hr. So you can put the value and you can find out the maximum range for which the transmitting antenna having height this and receiving a height this, when we are communicating from point to point. So what next question is, what will be the height of receiving antenna if it is located at 40 kilometer from the transmitting antenna and height of the transmitting antenna is 80 meters. So we can find out d is equal to what? D is equal to 4.12 into in bracket under root ht plus under root hr. So you can put here the value of ht and hr. You will get here, you can put the value of d, ht, and you can find out hr from this equation. So put all these values and you can find out hr, that is equal to what? 0.62 kilometer. Now sky wave propagation. So sky wave propagation is also known as ionosphere propagation. Sky waves operate between the frequency 3 to 30 megahertz range, and that are also known as short wave propagation. And electromagnetic waves at some angle from Earth's surface are known as sky waves. The sky waves travel into the space and are reflected back from the upper layers of the atmosphere, that is known as ionosphere. The sky waves above 30 megahertz not useful for the ionosphere propagation, they penetrate into the sky. So long distance point to point communication is also possible, and that is also known by using point to point communication. In a single, next point is, in a single reflection from ionosphere, the distance is more than 4000 km. Signal received due to the skywave propagation are subjected to fading due to the ionosphere condition, and these conditions vary from day to day or time to time or hour to hour along with the weather conditions. So skywaves are thus less stable than the ground waves. So atmosphere receive sufficient energy from the sun, producing positive and negative ions for long periods. There are several in this space, in this skywave propagation. So there are several layers at differing heights which reflect back to back the high frequency waves to Earth. So this is the structural details of the ionosphere. So here is your Earth. Now 50 to 90 kilometer, here you have several layers. This is troposphere, this is D layer, this is E layer, this is F1 layer, this is F2 layer. So these are the layers according to the distance. So 250 to 400 kilometer, your F2 layer, 140 to 250 kilometer F1 layer, 90 to 140 kilometer E layer, 50 to 90 kilometer D layer. Here is your troposphere, this is your Earth. So 4 main ionosphere layers above the Earth. Now D layer is what? It is the largest layer adjusting at the height of 50 to 90 km above the Earth with an average of 10 km. The degree of the ionization depends on the altitude of the sun and hence it disappears at night. It is less important for high frequency propagation, reflects very low frequency and low frequency waves, absorbing medium frequency and high frequency waves to a certain extent. So this is your D layer, and E layer, it appears at a height of 100 km and has a thickness of 25 km. So it disappears at night like the D layer, as we have studied in the D layer. It is also disappear at the night time because of the absence of sun at night and no radiations. The main function of this layer is to add medium frequency surface wave propagation a little and reflect some high frequencies in the daytime. Now the third one is E2 layer. It is very thin layer of very high ionization density and it is also called sporadic. E layer and often persist at night. So it has no role in the long distance communication but provides good reception over large distance. Now, the next is F1 layer. It exists at a height of 180 km in the daytime and has a thickness of 20 km. At night, it combines with F2 layer. Most of the high frequency waves passes through it and get reflected from the F2 layer. And the next one is F2 layer. It is the most important reflecting medium for high frequency radio waves. Its height is 200 to 400 km in daytime and a thickness of 200 km. At night, its height falls to 300 km and combines with the F1 layer. So these are the functions of these several layers. Now, reasons for F layer persisting at night. Since it is a topmost layer and it is highly ionized, and in spite of recombination ionization, it persists to some extent. And although ionization density is high in this layer and actual air density is not, and most of the molecules are ionized. Next is because of the low density also the molecules have a large free path, the molecular collision rate is low, hence the ionization does not disappear as soon as the sun sets. So reason for better high frequency reception at night is the combination of F1 and F2 layer into F layer and virtual disappearance of the other two layers which has caused noticeable absorption during day. Now electron density. Now here this figure shows the approximate distribution of the electron density among various regions and layers of atmosphere by day when the atmosphere is exposed to solar radiation, and at the night the last two layers merge into a single layer at night time. Now here you can see the structure. This is electron density, this is amplitude in kilometer. Now here this is D layer, E layer, F1, F2. So this is the daytime when you have 50 to 90 altitude in kilometers, then your D layer 100 altitude, then E layer 200, then F1 400, then F2. If we are talking about here electron density versus altitude in kilometer, now here heavy side layer that is at 100 and 100 to 200 that is E layer and 250 to 400 that is F layer. So this is the relation in between electron density and altitude in kilometer. Now, critical frequency. So, vertical incidence I is equal to 0 and so on, that is equal to 0 at the reflection point. In case of this vertical incidence, the maximum frequency that will be reflected back to the earth from an ionosphere, that is known as critical frequency of the layer, and it is denoted by Fc. So, critical frequency is different for different layers and that is denoted by Fc, and as you all know, this is the previous, as we have done in the previous, that n is equal to sin I upon sin r. So you can put here the value and you will get here the under root 1 minus 81 n upon f square. So when I is equal to 0, n is equal to n max and f is equal to fc. So n is equal to sin 0 degree upon sin r. So you can put here this equation to this one and you will get here I is equal to 81 n max Fc square. Now finally, this is the equation of critical frequency. Fc is equal to 9 under root n max. So Fc is expressed in megahertz and n max in per cubic meter. So Fc is the critical frequency. Now thank you for this video lecture.